Hey everyone, and welcome to this explainer. You know, have you ever looked up at the night sky and wondered if we could just perfectly map out the future of the entire universe? I mean, we're actually really good at predicting a lot of things, like exactly when the next solar eclipse is going to happen or when a comet will swing by. But there's this massive cosmic mystery that has completely stumped the absolute greatest scientists for centuries. Today, we're going to unpack a fascinating new way to finally make sense of how the universe moves.
Picture this for a second. Imagine 5 massive planets all grouped together out in space, constantly pulling on each other with their gravity. It sounds kind of like something out of a sci-fi movie, right? But the crazy thing is, when you get 5 objects interacting like this, their paths become this wild, unpredictable dance. It's just pure chaos. And for hundreds of years, predicting exactly where those 5 planets will end up over a long stretch of time, well, it's been practically impossible.
Okay, let's dive right into this and untangle the puzzle. Here's our roadmap for today. We'll cover the existing 5-body problem, the THD hypothesis, structural pressure, testing the theory, and finally, the real-world impact. Starting off with Section 1, the existing 5-body problem, and why chaos rules the cosmos. So, to fix a problem, we obviously first have to understand the brick wall scientists keep hitting, right? Well, here is the existing understanding of the issue. If you've got 2 planets orbiting each other, the math is honestly pretty easy. Even 3 objects can be tracked reasonably well for a while, but the second you add up to 5 objects, the whole shebang just breaks down. The math turns into this messy, unpredictable knot. A microscopic, and I mean tiny change in where a planet starts will completely change where it ends up just a few years later. It's literally like trying to predict exactly where a single drop of water will end up inside a crashing wave. Moving right along to Section 2. The THD hypothesis solution, a totally new way to look at the math. The specific framework we're exploring today is a real game changer. It's called the Triune Harmonic Dynamics, or THD hypothesis. This brilliant new approach was researched and authored by Kevin Brown, who is a researcher, inventor, and author. Instead of just trying to force computers to guess where planets are going to go using the same old rules, the THD hypothesis says, hey, we need to look at the actual stress building up within the system itself. Now, what's really interesting here is what Kevin Brown states. The 5-body problem accumulates measurable structural pressure. When this pressure exceeds a critical threshold, the system must undergo a structural transition. That word, right there, pressure, is absolutely the secret to solving the chaos. It means the system isn't just randomly bouncing around for no reason. It's actually building up tension over time until the rules themselves literally have to change. That brings us to Section 3, Phases of Structural Pressure, how the system bends before it breaks. You see, the math doesn't just fail instantly all at once. According to the research, it struggles through 3 very distinct steps. Step 1 is the base phase. This is just normal gravity doing its thing, and our predictions work totally fine. Then, Step 2 is the pressure phase. This is where the planets start pulling on each other in weird ways and chaos starts to really build up. Finally, we hit Step 3. The integration phase. At this point, the tension is so incredibly high that the old rules fail entirely, and the system either adapts into a brand new, stable pattern, or it just completely breaks apart. Let's define this clearly so it makes sense. Structural pressure is the measurable stress that builds up when predicted paths wildly drift apart and the current rules just no longer work. Think of it exactly like stretching a rubber band. You can stretch it for a while, right? That's the base phase. But as you pull harder, you start feeling that tension fighting back. That's your structural pressure. Eventually, you stretch that rubber band to its absolute physical limit. At that critical threshold, it doesn't have a choice. It must either snap or fundamentally change its shape. So, how do scientists actually know when the theoretical rubber band is about to snap? Well, they look for warning signs. These include things like frequent anomalies where planets just aren't behaving as expected. You'll see paths wildly drifting apart from where the computer thought they would go. You might even spot repeated clustering patterns where planets briefly group together in really odd ways. And you'll definitely see a steady growth in prediction errors. Basically, these are the red flashing warning lights on the cosmic dashboard. Now, these stress factors don't just happen in a vacuum. They all combine together. We've got our drifting paths, repeated clustering, and prediction errors all making up a sort of giant pie of chaos. And the THD hypothesis actually takes all these variables and combines them into one measurable pressure index. This is huge because for the very first time, it gives researchers a mathematical way to actually track the chaos as it grows instead of just throwing their hands up in the air and giving up. All right, Section 4. Validation and falsification, putting the theory to the test. So the crucial point is that a good scientific hypothesis absolutely must be testable. We have to know if it's real. Here is exactly how scientists can validate the THD hypothesis or definitively prove it wrong. For validation, the theory is proven correct if, as pressure hits that breaking point, we start seeing distinct clusters, repeating patterns, and totally new rules of stability emerging. The system basically finds a new normal. On the flip side, the theory is falsified if the structural pressure just stays high forever and nothing ever changes, transitions, or forms new patterns. It's a very clear line in the sand for scientists to look for. If we were to run a computer simulation, let's walk through the timeline of what one of these tests actually looks like. Step 1. Scientists observe the planets wildly drifting. Step 2. They use the math to measure that rising structural pressure. Step 3. They watch the system cross that critical threshold, the snapping point of the rubber band. And step 4, they record the structural transition, witnessing exactly how the system reorganized itself into something new.
And finally, Section 5. Real-world implications. Why this matters for us.
And this brilliantly illustrates why Kevin L. Brown's research is so powerful. The math of structural pressure doesn't just apply to gravity out in deep space. In space exploration, we can actually use this to safely plan swarms of satellites without them eventually crashing into each other. In technology, we can use it to manage highly complex, distributed artificial intelligence systems that might otherwise become totally unpredictable. And get this, even in economics, can use this exact same framework to predict limits and breaking points in stock market volatility. Talk about a multi-tool.
So what's the big takeaway? This represents a massive shift in how we think about the world. For centuries, science has been obsessed with finding exact, perfect predictions for everything. But the THD hypothesis tells us we need to shift from seeking exact predictions to mastering structural classification. In simple terms, we need to stop trying to guess exactly where a planet or a satellite or a stock price will be in a million years. Instead, we just need to learn how to predict when the rules of the system are about to bend, break, and change. To wrap things up, I want to leave you with this really provocative thought. If structural pressure rules the planets and actually helps us understand the greatest mysteries of the cosmos, what other chaotic systems in our everyday world are just waiting to snap into a new shape? Think about the complex systems around you, whether it's traffic, the weather, or even human behavior. Is the pressure building? Thank you so much for joining me for this explainer. Keep learning, keep asking those big questions, and I'll catch you next time.